Welcome to Wolfram Language, Developing with Devices. The Wolfram Language provides a streamlined framework for connecting to external devices. Today I will be guiding you through a variety of tutorials featuring different devices, boards, and hardware, all interfaced using the Wolfram Language. The first presentation I'm going to share with you is featured at our Wolfram Technology Conference. Let's join the presenters, Todd Gailey and Christopher Wolfram, as they describe the AR.Drone quadricopter and the development of the connection for controlling it.
I'm Todd Gailey, this is Christopher Wolfram. We're going to present today a Mathematica application for controlling the AR.Drone quadricopter from Mathematica. All right, so this is the drone. It's a recreational, hobbyist level quadcopter. It uses Wi-Fi interface for remote control. That's what we'll be using to communicate with the drone. It has two cameras. The one in front is a 720p HD camera. It's got one on the bottom. It's a very small thing here, that downward-facing camera that it uses for stabilization against the ground image. It has 3-axis gyro, 3-axis accelerometer, 3-axis magnetometer. It's probably got more sensors on the thing. It has an internal air pressure sensor, and it also has this ultrasound sensors on the bottom for detection of its height off the ground. It does have a very slick iPhone app and I guess an Android app as well for piloting the thing, which we won't be using, of course. And you can take off this outer styrofoam shell for outdoor flying. And it's just this cute little thing with just the 4 rotors. And it really zips around outside without the shell. It really flies well. So Parrot makes the C language SDK available to developers. It's Linux only at the moment. Eventually, I'm sure they'll come out with the Windows version. I don't know about Mac OS. There is a Java-based SDK for Android developers that's coming, but it's not available yet. For the 1.0 version of the drone, there were several third-party libraries, one in Java, one in .NET, to control the drone. And Christopher and I worked a while back, just very briefly, with the Java and .NET libraries. They seemed to be kind of flawed, and we had limited success. But I didn't have a drone at the time, so I really couldn't debug it very carefully. But in any case, they don't work for the 2.0 version of the drone. So we're stuck with the C language SDK. So given that I'm going to make a connection with the C language SDK, there's 2 obvious technology choices for connecting to this thing. And this is a quiz. What are they? MathLink and LibraryLink. All right, so in MathLink, we'd create some template file that would map Mathematica functions like drone connect, drone hover into some C language stub functions. And then we'd have to write those C language functions. We'd use MathLink API calls to read arguments off the link. We'd call the drone SDK functions, and then we would use MathLink functions to write the arguments back on the link. So some of the pros of the MathLink, well, 1, I already know how to do it. 2, the drone program runs as a separate process, so it can be killed and restarted without affecting the Mathematica kernel. Crashes in the program, won't crash Mathematica. Now it turns out, for various technical reasons, that it's kind of nice to be able to kill the drone process and start it again. Because of the way the drone SDK works. It's really designed to be used as an application. So within 1 session, it doesn't really work to connect, disconnect, connect again. The cons of a MathLink connection: well, it's not the fastest possible method. And in particular, thinking about the streaming high-definition video into Mathematica, maybe there's some issues with that. All right. So LibraryLink. Well, if you use LibraryLink, then I would write some C language stub functions again that use the LibraryLink API to read arguments off the link, call the functions for the drone, and then write results back to Mathematica. And then those C language stub functions are mapped to Mathematica functions via a Mathematica function called library function load. So the pros of this, well, for one thing, I actually want to gain more experience with LibraryLink. Now, I've written LibraryLink extensions. I've written LibraryLink extensions that ship with Mathematica. But I'm not an expert, so I thought I want to do some more with LibraryLink. Another pro is that there's extremely fast communication because the library runs inside the Mathematica kernel process. In particular, what's very fast is moving large arrays of data between the C program and the Mathematica kernel. They can share memory, so it's very, very fast. And I thought that might be useful for the video. And another nice little tweak is that we can use a push style of communication where the C code can poke data into Mathematica rather than Mathematica having to continually poll the C code to ask for the data. And we'll use that for the navigation data. The cons, are bugs in my program, or of course I mean bugs in the parrot stuff, can crash the kernel. And obviously that happened many times in the development of this thing. Okay, so now, this is an example of one of the simple functions in the C code for the link. It's called emergency. Now, I'm sure we won't have to call this function, but it's there, just in case. Now, there's an emergency function in the drone, and this is a very simple call. We just call m_argument get integer to get the arguments from the link, from Mathematica. Then this line in blue is really the only line in here that's not a library link-ism. This is the call that actually goes about and calls the function in the drone stuff. And then I call set integer to put a result back, and I return. So this is a very stylized thing. I showed this in my earlier talk in connectivity as an example. All library link functions look essentially like this, with the blue guts different from one case to the next. It's very straightforward. All right, so then what does it look like in Mathematica? I'm going to sort of walk up the chain from the C code into the Mathematica layer. So in Mathematica, I have this line, which calls library function load. So find library finds the library, and library function load loads that C code into Mathematica as a defined Mathematica function. And the arguments here are me telling library function load that this function takes an integer and returns an integer. And so it's called emergency func. And then really the drone emergency top level function that's exported from the package is just a one-liner. It just calls this emergency function thing with an argument. So that's, for a very simple function, that's the stack of code. There's one interesting aspect that one of the main reasons I wanted to use library link, because there's this technique that you can use in library link where you can create something called an asynchronous task. So that's what this function here is doing. It's creating this asynchronous task in C, which is basically a thread. You don't have to worry about what's actually happening here with any of the arguments, but there's a way to create a thread in the C code that runs, and then periodically, in the body of that thread, I have something that looks like this. And again, you don't have to care about the details, but I'm creating something called the data store. I'm populating it with data, and then I call this raise async event function, which is a callback into Mathematica. This is sort of the name of the event, and this is the data store. This is the data I put in, which arrives in Mathematica as a list of rules. So in the thread, and this is happening 30 times a second, it's poking this nav data into the Mathematica kernel. So rather than having some loop in Mathematica that's polling the data, I can just poke the data. And so if people are interested in programming things that, like a data feed or something, that you ready to try this?
I'm like speed doing this. Take off.
All right, here we go. It's flying.
And I can make it land. All right. Now let's try. Let's make it do something cooler. I'm gonna make it try and follow a path. So first I have to write the path out, which I had written down here, but now I don't have it. So okay.
So what you have is a path like this that Christopher's generated, and written a function called drone fly path that is going to cause the drone to go on that route.
Is that in yards or?
It's in magical units.
It's an undefined drone unit.
1 unit is the maximum speed of the drone in whatever direction it is for 1 second. So it's maximum speed for 1 second. So yeah, it's okay. You ready? I'm about to start it. Todd?
I'm ready. Oh yeah, I'm supposed to run herd on this thing. Make sure that it doesn't.
Taking off. Flying the path now. It's gonna go there. It's gonna go up and then down and then.
All right. Thank you for that.
Thanks to Todd and Chris for that fun and informative demonstration. If you haven't ever attended the Wolfram Technology Conference, I hope you'll consider making the trip this year to Wolfram World Headquarters in Champaign, Illinois. The 2014 conference dates are October 22nd through 24th, which is a Wednesday to Friday, and more details will be available soon. The Technology Conference is the best time to meet our Wolfram experts and other users in person, making it the ultimate geek-out opportunity. Moving on to our next device, late last year we were excited to announce the availability of the Wolfram Language and Mathematica on the geekishly awesome Raspberry Pi. This low-cost, credit card-sized computer is an engaging way for almost anyone to start coding using the Wolfram Language, and its small scale demonstrates the ability going forward to embed the Wolfram Language in pretty much any new device or system. There are countless possibilities for interesting experiments and explorations using the Raspberry Pi, and Wolfram Community is a great place to get ideas and view postings by other developers. This next tutorial by Arnaud Busing gives step-by-step instructions for getting up and running quickly using the Wolfram Language on the Raspberry Pi, and features several example postings from Wolfram Community. Here is Arnaud.
First, let's quickly review how to get Mathematica on your Raspberry Pi. If you have not yet installed Linux on an SD card for your Raspberry Pi, then you can go to the Raspberry Pi Downloads page and download the latest version of their Noobs installer tool. As of January 9th, Mathematica is included in the recommended Raspbian Linux option of this Noobs installer tool. Simply follow the instructions from the Raspberry Pi website and you're done. If you already have Linux running on your Raspberry Pi, then you can install Mathematica and the Wolfram Language by typing the command shown on the screen at the terminal prompt and following the instructions shown on your terminal. To start the Wolfram Language, open a terminal window on your Raspberry Pi or use a tool like PuTTY to log into your Pi from a Windows machine. On a Mac you can also use your terminal app to log into your Pi using the secure shell command SSH. At the terminal prompt type Wolfram, which will launch the simple text interface to the Wolfram Language. After a few seconds you will see an in prompt appear. This is the place where you can enter any Wolfram Language command, for example 2+2. Once you've typed a complete command, you can hit the enter key to send the command to the Wolfram engine for evaluation. In simple cases the answer will appear almost instantaneously. In more complicated evaluations, the answer may take a few seconds. If an evaluation takes too long, you can press Ctrl+C to interrupt the Wolfram engine. This will bring up an interrupt menu where you can type abort to abort the evaluation or exit to exit the Wolfram engine. Here are a few more examples of some basic functions in the Wolfram Language. Solving equations. Solving integrals. Computing the average of a list of numbers. Factoring integers. Manipulating strings. And manipulating expressions. All in all, there are over 4,000 Wolfram Language functions, and they are all documented online at the location shown on your screen. If you want to run the same set of commands repeatedly, you can also place them in a text file and execute them by launching the Wolfram Language in script mode. In this example, I create a new file called example.m and enter one print command in it. I then save the file and run it by giving the Wolfram command the -script option with the file name. Now let's take a look at Mathematica, the desktop user interface to the Wolfram Language. For purposes of this recording, the Raspberry Pi desktop is running as a remote desktop in a VNC viewing session. You can launch Mathematica by typing Mathematica at a terminal prompt or by double-clicking the Mathematica icon on your desktop. The startup sequence for Mathematica takes about 25 seconds when you run your Raspberry Pi at its regular, non-overclocked CPU speed. For the purpose of this recording, I have already launched Mathematica. The Mathematica user interface adds many useful features that the Wolfram Language terminal interface does not provide. Most notably, all the visualization and dynamic functionality works within Mathematica, whereas it does not do anything useful in the terminal interface. Let's take a look at a few visualization features. First, a simple two-dimensional plot. Next, let's try to do a three-dimensional surface plot. Mathematica also comes with a dynamic interface, which allows you to build interfaces which update as you interact with controls such as sliders, buttons and input fields, or as variables are updated as part of a scheduled background task. Here are some simple examples. First, let's evaluate dynamic of x, which initially will just display x, but will change whenever x changes its value. So now let's change what x is. For example, we can set x to be 42. And notice that the dynamic output is now also 42. Or we can set x to be a graphics expression. And note how the dynamic expression updates at the same time. Now let's go one step further and create a button which sets x when you click the button. So now let's look at a few examples of how to use Mathematica to interact with hardware on the Raspberry Pi. The simplest case is probably the Raspberry Pi camera board. It can be purchased at online hardware vendors such as Adafruit.com. I mention this particular hardware vendor because it also offers great online support to get your hardware connected to your Raspberry Pi. The Raspberry Pi camera board costs about $30 and is a fun piece of hardware that is well supported by Raspberry Pi and Mathematica. To take a picture with the camera, you can use the device read function in Mathematica, which is a wrapper around the RaspiStill command line utility. Here's an example. If you want to take a larger image, you can specify the image dimensions as a second argument, like so. You can also take pictures every few seconds by running a scheduled task. Next, let's take a look at a GPS device. In this case, I'm using a GPS module from Adafruit, which can be used on both Raspberry Pi and Arduino boards. This GPS module costs about $40 and comes with setup instructions on the Adafruit website. This particular GPS module works as a serial device. The moment it powers up, it will begin tracking GPS satellites and start to generate textual GPS data on the serial link. On the Raspberry Pi, there are two ways to make a serial connection to the GPS module. The simplest way is to use a USB to serial adapter cable, which does need to be purchased separately. The second way is to connect the GPS device directly to the GPIO pins of the Raspberry Pi. In this case, you will need to modify the Linux boot options, which is clearly described on the Adafruit website. If your GPS device is connected and working, start Mathematica and open the device on your serial port. In my case, I'm using a direct connection to the GPIO pins, which means I need to use the dev TTY AMA 0 using a baud rate of 9600. The next step is to read the serial buffer. This will return a list of bytes which can be converted to plain text using from character code. The next few steps all revolve around cleaning the data to extract the GPS latitude and longitude. This step imports the full string as lines of GPS codes. This step extracts just the lines that have GPS coordinates in them. This evaluation imports just the GPS coordinates with their latitude and longitudes, north and west. After we've extracted the key GPS data pieces, we need one more small algorithm to convert the GPS device data format to regular decimal latitude and longitude coordinates. For this, I've written two helper functions, a convert function and a coordinate function. The convert function converts the GPS format to a regular decimal format, and the coordinates function converts both latitude and longitude and adds a minus sign as appropriate for north and south and east and west. And this gives you the final result, which is the location of the GPS device. Finally, we close to the serial connection. So these are a few examples of what you can do with the Wolfram Language and Mathematica on your Raspberry Pi. But there are many more interesting examples on the Wolfram community, which is a large user forum with questions and their answers, comments, ideas and suggestions for the Wolfram Language. Specifically, there is a group on the Wolfram community dedicated to Raspberry Pi specific questions, including installation questions, programming questions, and up-to-date product information. I would like to take a few minutes to show you some interesting posts made recently by some of our users. In particular, there are two people who have made spectacular posts on the community, namely Bob Lesueur and Diego Svijovic. Since this talk is pre-recorded, I don't know if they're currently watching this screencast, but I want to thank them for making such interesting posts. This is the main page for the community forum for the Wolfram Language and Mathematica. To help create structure, this forum splits out into different groups for different top-level interests. Let's take a look at the Raspberry Pi group. Here we see individual posts with people asking questions, reporting issues, and sharing some of their ideas and experiments. The first post I would like to share, by Diego Svijovic, is about measuring the acceleration of a ball rolling down an inclined plane. Diego uses Lego for the physical setup of the inclined plane and an Arduino Uno connected to 3 light sensors to detect elapsed time since the ball was released. The Arduino talks to the Wolfram language running on a Raspberry Pi over a serial connection. The Wolfram language code also creates a button which initiates the start of the experiment by releasing the ball. When the data is collected, Mathematica creates a graph with 3 data points, which can then be used as a starting point to test any hypotheses about the physics underlying this experiment. And here it is in action. Another really cool example is from Bob LeSueur, who posted how to build a rudimentary spectrophotometer. All the details are on his blog page, linked from the community page. This setup shows how to build an instrument used heavily in chemistry, biology, and astronomy to determine what substances are present in a sample material. Without going into enormous amounts of details, Bob also uses Lego to create his experimental setup, which includes a bright white light source, a magnifying glass to focus the light on a piece of an old compact disc, which acts as a diffraction grating. This is mounted on a stepper motor, which slowly turns while the light sensor detects the light that is filtered through a liquid and transparent example. This data is then recorded and visualized in Mathematica by using a list plot on the data. The Raspberry Pi website itself also has resources to help you get the most out of using Mathematica on the Raspberry Pi. This website also has a forum with a group dedicated to Mathematica questions. Both the Wolfram community and the Raspberry Pi Mathematica forum are regularly visited by Wolfram employees to help with questions and post product updates when they are available. The Raspberry Pi website also has a blog where we aim to have regular guest posts which bring product updates and summarize the activities around this product. I need to point out that one place not to look for support is the regular Wolfram Premier Service support, since this service is dedicated to our commercial offerings of desktop Mathematica and is not intended for the free Raspberry Pi version of Mathematica.
This last tutorial I want to show you visualizes a potentiometer connected to another device, the Arduino Uno microcontroller board, using the Wolfram language. Here is our node again.
What we're going to do today is connect a potentiometer to an Arduino Uno, which is then connected via a serial connection to Mathematica running the Wolfram language. There are a few basic steps we need to follow to get to the point where we can visualize the potentiometer setting inside Mathematica and the Wolfram language. The first step is the hardware requirements and setup. Once that's set up, we need to write an Arduino sketch which reads from the analog input and writes to the serial device. The next step is to set up a connection to the serial device from the Wolfram language. We then need to repeatedly read from this serial device, and we do that by scheduling a repeated task. And finally, we'll be using a function called angular gauge in the Wolfram language to visualize the data stream as you manipulate the potentiometer. To set up this experiment, we need the following hardware. We need one Arduino Uno, we need a breadboard, jumper wires, a potentiometer, and a USB cable to connect the Arduino to your computer. First, we'll connect the potentiometer to the breadboard. The potentiometer has 3 pins, one for voltage in, one for grounding it, and the one on the opposite side has the variable voltage, is connected to the variable resistor. We put in 3 jumper cables, 2 on one side and 1 on the other. Then we connect the first one to the 5-volt out, the yellow one goes to the ground, and the purple one goes to the A0 input sensor. With the hardware setup completed, we now have to write the sketch that's going to take care of the Arduino side of the serial connection. Everything is done on the analog pin 0, which is defined by this pin variable, and the second variable is val, is going to hold the red value from the pin. We have to set the pin as input, which is done with pin mode function here, and we have to start the serial connection on the Arduino side. Then the final section loops continuously and reads from the pin a value. Now this value is in the range from 0 to 1023, so we have to divide by 4 to get it into a byte value, which goes from 0 to 255. So with this code all set up, we can upload it by hitting the upload button, and that should set up our Arduino sketch on the Arduino Uno. With the hardware setup completed and the Arduino sketch uploaded, we now switch to the Wolfram Language side of this project. And the first thing we need to do is open serial connection, and we do that by using the device open function, and the first argument specifies the type of device, which in this case is serial. And then the second argument has to specify a port, which is machine specific. I'm using COM4 here because I'm using a Windows machine. And I'm specifying a baud rate of the same baud rate that I use for the sketch. They have to match. For Raspberry Pi users, it's the same command. The only difference is that you need to give a different device, in this case /dev/tty-acm0 if your Arduino is connected to a USB port on your Raspberry Pi. The next step we have to do is schedule a task which runs several times a second. In this case, we're using run scheduled task, which runs every 0.05 seconds. So it runs 20 times a second. And what this scheduled task does is read the entire buffer of bytes from the serial connection and returns the last one. So it gives the most current value and it sets it to the Wolfram language symbol val. The statement above here just makes sure that previous scheduled tasks are removed, so that repeated evaluations of run scheduled tasks don't all run together. That then they would all be executing and reading from the same buffer. This makes sure that there's only one scheduled task accessing the serial device at any given time. Now with this scheduled task running, I can evaluate this angular gauge expression, which is going to dynamically update every time val changes. So here's the potentiometer setup on the right, and on the left is the corresponding angular gauge. So when I turn the potentiometer with my hand over here, the angular gauge will change value at the same time. And as you can see, it goes all the way up to 255, which is the maximum value. And it goes all the way down to 0, and you can turn it exactly to a particular setting, like for example 100, if I can reach it, or you can go to 200. So that's a very simple example that you can do yourself with an Arduino. That's really all you need, and a few small pieces of hardware, and Mathematica to visualize your hardware device emulated in software.
I hope these tutorials have provided some inspiration for your own development with devices.